Howdy, this is your friendly neighborhood physics teacher here, and we're going to start going over the free responses for each of the units. We're going to start with Unit 1. So this is the free responses on your College Board classroom, and we'll just start with Unit 1. When you see, it says question 1. This question is a long free response question. Show your work for each part of the question. So that's with anything on the free response. You'll have about 5 different free responses with different parts. Like this one has part A, part B, part C, part D, and even part D has like a section 1 and section 2 to it. So this is typical for a free response. And make sure you don't just give the answer, make sure you explain. So this, you see a picture, if you have it up, you see a picture, pretty much have an incline, the ball rolling down it, and it goes down. Above the ball, it says cylindrical object. It labels the incline, and it calls it figure 1. So a cylindrical object can roll down an incline as shown in figure 1. The incline is slightly less than 1 meter in height. So basically what it's saying is right here, is a little less than 1 meter. A group of students wants to determine the acceleration of the object while it's rolling down the incline. The students have access to the following equipment. It says they have access to a stopwatch, which can measure time intervals to 999 seconds with a precision of 0.01 seconds. A clock, which can measure time intervals up to 12 hours with a precision of 1 minute, 60 seconds. A meter stick, which can measure up lengths between 1 meter with a precision of 1 millimeter, and a pair of calipers, which can measure lengths of 10 centimeters with a precision of 0.05 millimeters. If you don't know what those, it's like a little clamp you can clamp around small objects to measure them more accurately, so instead of trying to balance, trying to line them up with a meter stick. So part A says assume the object moves with a constant acceleration as it rolls down the incline. Write an equation that includes acceleration in quantities that can be measured or obtained from the measurements by using the available equipment. So let's think about that. So we have stopwatch. So stopwatch and clock, they both measure time. We have a meter stick and the little clamper thing. Those both measure distance. So we have to think about an equation that has time and distance and acceleration in the mix, because that's what we're looking for. Now, if you look through your formula chart, it's the second formula on your formula chart. Your second formula is x equals x naught plus v naught, or vx naught t plus 1/2 ax t squared. Remember, all these little sub x's are just telling you that it's in the x direction, which if we tilt our x and y axis will be in the x direction. So we can figure out, so x can stay because that's dealing with distance. Our x naught is just going to be 0 because it hasn't moved yet. So our x naught is just going to be 0. Our v naught, again, is just going to be 0. And we need acceleration and we need time. So our equation ends up being x equals 1/2 x ax t squared. So that's going to end up being our equation. And actually, if I can pull up the rubric for like what, if they actually scored this, what they would get, you would get a point for this, but then you get a point for saying that the initial velocity is 0. So showing that. Like I said, I keep saying, show every single step. You never know what you're going to get credit for. So just having the equation would just gotten you 1 point. But showing that the reason you don't have a velocity in this equation is because your initial velocity is 0. Showing that in some form or fashion, that was writing it down, showing kind of like doing this, you would have gotten a point. So part A was 2 points. Part B. Part B says, design an experimental procedure the students could use to measure quantities required to determine the acceleration of the object. In the table below, list the quantities and the associated symbols that would be measured in your experiment and the equipment used to measure them. Also, list the equipment that would be used to measure their quantities. You do not need to fill in every row. If you need additional rows, you may add them in the space below the table. It has a table and it says quantity to be measured, symbol of quantity, and equipment for measured. So A kind of helps us line up to B because we need to, so quantity to be measured, one of it is distance. We would need to measure distance. Distance is represented with an X. What you would measure distance with is a meter stick. Next thing we would need is time. We would use our stopwatch. The stopwatch is more accurate than the clock. And that, I flipped that. So the symbol that represents is T for time, and then we need our stopwatch. That's all we need to measure. So it gave us 1, 2, 3, 4, 5 things, but we only need to fill in two rows. So now it says describe the overall procedure to be used. Referring to the table, provide enough detail so that other students could relate the equipment, including any steps necessary to reduce equipment uncertainty. As needed, use the symbols to define in the table and or include simple diagram of setup. So they actually accepted two different methods. They actually accepted a paragraph form or procedure 1, procedure 2. I know I've been sitting there pushing procedure 1, procedure 2. The reason I do that is so you actually think about every single step. Once you sit there, start writing a paragraph, you might forget things. So an example response paragraph form would be mark the position of the object in equal time intervals as measured by the stopwatch as it rolls down the incline. Measure the position of the marks using the meter stick. Repeat the procedure for 3 trials. Or you have your step 1, step 2, step 3, step 4. So step 1, mark the starting point near the top of the incline where the cylinder is to be released from rest. See, need to remind you, don't need to push it, just from rest. Step 2, use the meter stick to mark off distances of 30 centimeters, 60 centimeters, and 100 centimeters from the starting point. 3, use a stopwatch to time how long it takes the cylinder to reach the 30 centimeter mark after it is released from rest at the starting point. Repeat step 3 for a total of 3 trials. Repeat step 3 and 4 for 60 and then 100 centimeter marked. The total of 3 trials for each mark. So again, kind of stepping through and letting them know you have to do 3 trials for the 30 centimeters, 3 trials for the 60 centimeters, 3 trials for the 100 centimeters. So it's just writing down a procedure, what we've done in every single lab. Part C. What quantities would be graphed to yield a straight line or a linear line that would be used to determine the acceleration of an object? Only indicate quantities that either were measured in part B or could be determined from quantities measured in part B. So you can only use quantities in part B. So that's it. So since we can only use things we measured, we only measured two things. So we measured distance and we measured time. So we know that we're using distance and time. But it was kind of wanting us to say which one would be the vertical and which one would be the horizontal. And how would the graph be used to analyze the data to determine acceleration? So if you think about drawing a graph here, I'm going to give you a hint. Time is always on the x-axis. So it'll be time, distance. But if we look at our equation, x equals 1/2 ax squared. Time is squared. So do you think that plays a part? You better believe it. So you would have to graph your t squared. The reason you have to graph that t squared is so you would end up with a straight line. You would end up with a straight line. If you don't do the t squared, you're going to get some curve. So that t squared matters. So again, your equation. So part C, we're using part A. So always go back to your different parts, and we're even using part B. So your x-axis would end up being t squared. Your y-axis, or your horizontal axis, would end up being t squared. Your vertical axis will end up being x. And then I'm just kind of expressing that. So your x and your t squared have a direct relationship. Yeah, that's all you would have to sit there and explain. You would get so you got a point. Okay, so point can be earned from choosing appropriate quantities that relate on the graph as a straight line. So, yep, there you go. Get a point for writing that down. Part D. Oh, that was CI. So that's CI. Let's go back up to see what C2. Okay, C2 is how could this graph be used to analyze the data to determine. So this one is again, so in this one we used, this is CII, we used X is proportional to t squared. Basically, so that means you're stating your slope. It's going to be what's left over. We use that, so that's left over. So your slope would be 1/2 of your acceleration. And then you're just comparing, so the acceleration is twice the slope because of that lovely 1/2. So you got a point for indicating that the acceleration could be determined by the slope, and you got a point on correctly indicating how the acceleration could be determined. So you got a point for this, and then you do get another point for stating that your acceleration has to be double. The reason it has to be double is because of this lovely 1/2 right here. There we go. Now we're part D, part DI. So part D, you see 3 different figures. You see, so the ball is not on the ramp anymore. So you see the ramp over here. But the ball is here going towards a wall. And then you see the progression of that. You see it here, you see it here. So if this was part 1, part 2, and then technically part 3 would be it bouncing over here. So part 4 says, after rolling down the hill, the central object rolls across a horizontal surface as shown in figure 2A. The object then hits a vertical wall, figure 2B, and bounces off the wall with the same speed as it did before it hit the wall, figure 2C. Note that during the bounce, the object is in contact with the wall for a time interval that is very small, but not 0. So it's saying it's a very short time it hits the wall. DI on the dot below, which indicates the object during the time it is in contact with the wall. Draw an arrow showing the direction the object's acceleration during the bounce. So this is kind of like a free body diagram, but we're just showing a vector of acceleration. So it gives us the ball, and we're supposed to show, so draw an arrow showing the direction of the object's acceleration during the bounce. So it's in contact with the wall. So it goes and hits the wall. So as it's in contact with the ball, or the wall is having to put an acceleration this way, because it was going this way, and now it's going that way. So for it to change, the wall has to be put in acceleration, which we now know is net force, or your normal force, the opposite way to counteract that acceleration. So you got a point for just drawing a left arrow. Part DI says during the time the object is in contact with the wall, is the magnitude of the acceleration greater than, less than, or same as it was while was rolling down the ramp? So this was DI. Now we're going to be doing DII. So the correct answer is greater. Greater than. So again, let's read the question again. So during the time interval the object is in contact with the wall, is the magnitude, so we're not worrying about direction, we're just worried about magnitude, of the acceleration greater than, less than, or the same as it was rolling down the ramp? So as it's rolling down the ramp, the magnitude of acceleration, it will meet its max acceleration at the bottom of the ramp. So even though it's rolling down, it's still going to be greater at the bottom. You got a point, so the sad thing is, if you just put greater, you're not getting a point. You have to sit there and explain. So you actually got a point for stating that the time contact is less than the time it took to roll down the hill. Because it's greater than, because we know that our acceleration is our change velocity over time. And since our time has decreased, that means our acceleration is increased. That is an inverse relationship. And then you gotta earn a point. So you got a point for kind of showing this, and you got a point for saying that it's an inverse relationship. That's why relationships are extremely important. So it kind of, something that you could have said, like an example is acceleration A is given by the expression, and you gave your equation, A equals V, change in velocity over change in time, where your change velocity is change in velocity, and your delta T is your time interval during the change velocity. So just kind of explaining, so you need to explain the equation. When the ball is released from rest at the top of the incline, change velocity represents the change in the object's speed from the top of the incline to the bottom of the incline. This change in speed takes place over a time interval, change in time. When the ball collides with the wall, the object's change in speed is twice as much as the first scenario, and the time interval in which the change in speed occurs is much shorter when the object is released from the top of the incline. Therefore, the acceleration is greater in the case in which the object bounces off the wall. So you can kind of show with the equation, or you can put it in words. whichever way is best that you feel comfortable doing. So that's number 1 of Unit 2. So number 2 of Unit 2. Again, it says this question is a short free response question. Show your work for each of the questions. So we are now in a complete different question. And it shows an astronaut on top of a hill. So basically, we have a hill, we have an astronaut, and the astronaut's holding a rock. It's saying from the rock to the bottom of the floor is 100 meters, but we also have a 15 meters per second pointing up. It says an astronaut holds a rock 100 meters above the surface of planet X. The rock is thrown upward with a speed of 15 meters per second, as shown in the figure. The rock reaches the ground 10 seconds after it is thrown. The atmosphere of planet X has a negligible effect on the rock when it's in free fall, so there's no air resistance. That's a fancy way of saying there's no air resistance. So AI says determine the acceleration due to gravity for the rock when it is on planet X. So we're looking for the acceleration of planet X. So we got to think about what we know. What are some known things? So we know that from here to here is 10 meters. Another thing we know is as it goes up and it comes back down. So if it's going up, so right here, we know its velocity is 0 up here, but we also know right here, its velocity is 15 meters per second down. Remember when an object's going up and coming back down, if you're at the same height, it's the exact same velocity, just different directions. So we don't even have to worry about this little extra jaunt there. So we're going to end up using, again, our second equation on the formula chart. I'm just switching it to y because we're in the y direction instead of the x direction. T 1/2 ay t squared. And we're actually looking for ay. So let's go ahead and manipulate it so we get ay by itself. So that's going to mean we're going to end up subtracting that over. Going to end up subtracting that over. So we get y minus vy naught t. Got the letters are squared there. Minus vy minus y naught equals 1/2 ay t squared. You know, multiply both sides by 2. And we can divide both sides by t squared. So all I did is got to get our a by itself. So we have 2y minus vy naught t, and this should be parentheses, minus y naught over t squared. So there we go. Now we just kind of plug in what we got. So t2 stays. Our final, so it's starting here, so it's at 100 feet, or 100 meters. So that means our final is 0. Our initial velocity was 15. Our time was 10, and our initial position was 100. And again, our time was 10. Can't forget about the squared. And all you got to do is plug that into your calculator. So we get, the 0 can go away. So we get 15 times 10, which gives you 150 minus 100. We can go ahead and do 10 squared. So 150 minus 100 gives you 50. So 50 times 2. So you're getting 1. I feel like I messed something up mathematically. I lost my negative. That's what I did. Psh. Right there. See, there's a negative here. That negative has to come down. I messed up right there, right there. So this is not 50. I was like, that should not be the answer. So you got to be careful. Cannot drop your negatives. It's really easy to do, as you can see. I'm actually kind of glad I did that. So you can see, remember, don't do that. I totally planned it. I didn't mess up at all. Meant to do that the whole entire time. There we go. That looks a whole lot better. So your acceleration is -5 meters per second squared. Remember, the negative is just telling you it's going down. Do-do-do-do. So there you go. Now all that work, right? Ready for this? You ready for this? So getting an answer with all that work, you got this problem was worth 1 point. And you got 1 point for correctly substitution of values. So you got a point here. So this is where you got the point. All this work, and you got a point there. Let's say you never know what the AP what AP is going to give you points for. So part AI says, how does the speed of the rock when it reaches the ground compare to the speed of the rock when it's thrown up? So we're comparing the velocities. So we know that as it's going up, it's 15. And we know that when it's going at the same height, it's going 15 down. So is that velocity going to increase or decrease? Because we don't necessarily have to figure out a number. It's just wanting us conceptually figure it out. Well, hopefully you got that your at the bottom is going to be bigger than when it was released. So at the bottom is going to be bigger when it's released, because, like, again, if you have 15 when it's thrown up, it goes 0 and it comes back to 15 here, then it's just going to keep getting bigger and bigger and bigger because of our acceleration pulling it down. And you have to explain. If you don't explain, you do not get any points. So if you just put that, or like, I think it was like a check, you had to check which one is correct. Is VD greater than VU, or is VD equal to VU, or is VD less than V? It's like a little check system, kind of like the ranking questions. If you just checked it and didn't explain, nope, no points. You have to explain. So again, that's kind of like when the rock's being thrown up, it eventually reaches max height, which is 0. It falls back down. When it reaches the same height, it's 15. So it just, it's that little explanation. You got to walk through it. So part B says, a student wants to know how the motion of the rock would be different if it was thrown upward at 15 meters per second from a height of 100 meters above Earth's surface in a clear cohesive paragraph length response. Paragraph length response that may also include figures and or equations explain how the motion of the rock on Earth would be different from the motion on planet X in terms of its max height above the ground and speed at which it would reach the ground, time at which it was in free fall, and the acceleration due to gravity. So the biggest thing here is that planet X has a acceleration of 5. Earth has an acceleration of 9.8. And again, yes, they're both negative because they're both being pulled down. Earth has a higher acceleration. So I'm going to put it in bullet points, but you needed to put it in paragraph to get full points. So big thing is, so if we talk about height, so that's the first thing it brings up, right? Yeah, so height. Your X compared to Earth, your X is going to have a greater height than Earth because it's not pulling as much, so your rock is able to go higher. And again, it all goes back to Earth having a greater acceleration due to gravity. Okay, so we have height, speed at which it reached the ground. So speed at ground, X compared to Earth, your Earth is going to have a greater acceleration when it hits the ground because you have a greater velocity when it hits the ground because you have a greater acceleration. Time in which in free fall. So pretty much how long is it going to be in the Earth? It's going to be in the sky longer for X, planet X versus Earth, because again, the acceleration isn't as high, so it's not going to pull it down very quickly compared to our 9.8, which is almost double. And then acceleration. Of course, Earth has a greater acceleration. So you've got a point for each of those stating that the acceleration due to gravity is greater on Earth, that the time would be less on Earth. You got a point for stating that the distance. Did it ask for distance? Did I miss that? Oh, that's probably height. Okay, so the max distance, there we go, above the ground would be less on Earth. And you got a point for saying that would reach the ground. The speed of the ground would be greater on Earth. And then you got a point. So if you're running short on time and you wanted to do this, you got a point for each one of those. But then you got one more point for putting it in a nice, pretty, cohesive paragraph. So if you're running short on time, listing it out like this will at least get you 4 points. You're just missing one out of the, so it's a 5-point question, you're just missing one. So write down something on your answer choices. You'd be amazed what you get points off. So that is Unit 1 free response. If you have any questions, please let me know. Have a wonderful day. Remember, you're loved and appreciated. Bye.